Hello?
Hi, Ali. Kate here. We have the data. I'll send you the files now to analyse.
Excellent. We'll get to work.
Okay, catch you later. Bye.
We've got a case on our hands. 2 mysterious exoplanets, and we need to profile them. Target A will be the giant Kelt 3b. This exoplanet is unlike anything we have seen in our solar system. It's a large, puffy gas world orbiting very close to its host star.
Compared to Kelt 3b, TOI 560c is almost tropical, though still too warm for we humans to go there for holidays, since it's still hundreds of degrees Celsius warmer than Earth. During the hackathon, you will analyze data from KEOPS to profile our 2 mysterious exoplanets, Kelt 3b and TOI 560c.
So could we use KEOPS to observe our exoplanets?
Yes, you'll be able to use the light curves that we get to help solve your case. I warn you though, it's going to take a bit of teamwork to hack the KEOPS data.
Great. We'll collect the details and get back to you.
Let's hack an exoplanet. Hi, I'm Katja. Welcome, Space Detectives. Thanks for joining us for the first ever Ease Education Hackathon for secondary students.
Hi, I'm Ali. Let's get to work on the case of the mysterious exoplanets.
Are you ready to solve the case?
Your mission is to analyse the data from the ESA KEOPS satellite and characterise the 2 mysterious exoplanets, Kelt 3b and TOI 560c.
We need your help to uncover some of these exoplanets' properties. What do they look like?
Are they big and made of gas, possibly even with giant rings like Saturn?
Or are they small, rocky and colourful like Mars?
Maybe they are completely alien and covered in water.
Or even icy frozen worlds?
Do these type of worlds even exist?
We need a great scientist to help us answer this question.
Like the scientist who designed the KEOPS satellite, Willy Benz. He's going to tell us the story of exoplanets.
My name is Willy Benz. I'm an astrophysics professor at the University of Bern in Switzerland, and I'm also the principal investigator of KEOPS mission. Exoplanets are planets that are not in our own solar system. They are planets orbiting other stars located anywhere in the galaxy. It turns out that we only see the ones very close to us. So compared to our own planets, they're very, very, very far away. And the only way we can study them is to look at them through telescopes. A planet, essentially, at least in the visible, just reflects the light of its star. And therefore, planets are much, much, much fainter than stars they orbit, typically 1 billion times fainter. So it is very, very difficult to actually observe, to see these planets. So we need to develop instruments that are quite challenging. They are so challenging that these instruments don't exist today. So people have invented other techniques to indirectly detect these objects. So we don't see them, but we see some effect of these objects. And there are 2 successful methods. Historically is the radial velocity method, a method where we monitor the velocity of the star, which turns out to wobble if a planet orbits the star because of their mutual gravitational interaction. So little velocity changes, periodic velocity changes of the star indicate the presence of a planet, and the amplitude of these changes will tell us something about the mass of the planet. So we have a way to detect them and to measure the mass. The other method is a transit method where we monitor the light we receive from the star. And if a planet passes in front of the star, it casts a little shadow, which means then, as seen from us, we see a slight decrease in the light of the star. And the decrease that we can measure tells us something about the size of the planet, because that's the amount of light that is blocked by the planet. This is typically what KEOPS is used to find and measure the size of the planets. So it is difficult, and it is so difficult that we had to wait quite a bit of time before the first planet was discovered, actually 1995, because before the instruments were not just good enough to measure these small effects. In 1995, when I visited during the summer the Geneva Observatory, Michel Mayor pulled me in his office and sort of told me, I have something to show you, very secretive and things. So we went to his office and he showed me a plot of these radial velocity changes of a star, 51 Pegasus, the name was, and he showed me that this is a planet that was creating this oscillation that is about half the size of Jupiter orbiting the star with a period of about 4 days. This was so revolutionary because, according to the theory of the time, giant planets were located far away, just like Jupiter. We had this template of our solar system, and this was so different that I didn't believe it at first. And so we had sort of a long exchange of argument. But in the end, he was so convincing that I had to give up. And in the end, of course, he was right. The data were what the data are, and clearly showed that there was a planet there. And this single discovery, this single object, sort of shattered the entire story of planet formation, because it simply shouldn't have been there. And the fact to find is precisely something that was impossible to exist was what shook the entire world, astronomical world, about planet formation. Okay, what do we want to learn about exoplanets? There are many things. Now we know that 5,000, a bit more than 5,000 exist, and they come in all different flavors. They are very different from the planets in our solar system. The architecture of planetary system is not at all looking like the architecture of our own solar system. So we discovered a lot of things already, but that's not enough. We want to know more. Now that we know they exist, we want to know what they're made of, how hot they are. Do they have an atmosphere? What is this atmosphere made of? Do they have also oxygen, nitrogen like we do on Earth? Or do they some methane atmosphere or some crazy things surrounding them? We want to know, is there water there? Maybe nice oceans, or not at all, dry land. And eventually, of course, the big question, the $1 million question, is there life somewhere else in the universe? So all this is something that's in preparation, because this requires, so to speak, the next generation of instruments to be able to do spectroscopy of these objects, to learn about all what I listed here. And the first step has started, is the James Webb Space Telescope that does spectroscopy of these transiting planets. So we start learning about them. And the next generation will be the large ELTs, the extremely large telescopes that are built on the ground, and possibly the giant space telescope of the future. So this is just beginning. For now, we just know they're there, and now we're curious. Planets are difficult to detect, so welcome to Hack an Exoplanet contest. Proud of you to take on this challenge, and I wish you all the best of luck.
Your mission begins now.
Let's begin the investigation with the giant Kelt 3b.
Gather your detectives team and work together to complete the missing information in the exoplanet case files.
Determine what type of exoplanet world the Kelt 3b is by analysing the Cheops data.
Can you find its size, orbital period, distance, density, and possibly its composition?
Make sure you have the documents you'll need at hand. You can find these on hackanexoplanet.esa.int, along with all the clues you'll need to complete your investigation.
Throughout the investigation, our exoplanet experts will be here to guide us, so don't worry. Once you are ready to start analyzing the Cheops data, jump to Max's explanation of how exoplanets are studied.
Good luck, detectives!